Welcome to the periodic table. Have you ever wondered what everything in the universe is made of? From the air you breathe to the phone in your hand, from the stars in the night sky to the very cells that make you, it all comes down to a fundamental set of ingredients called elements. And to keep track of all these amazing building blocks, scientists use a fantastic chart, a super organized map of matter called the periodic table of elements. It might look a little intimidating at first with all its boxes and letters and numbers, but trust me, it's one of the most powerful tools in all of science. It's more than just a poster on a classroom wall, it's a guide to the entire known universe. Think of the periodic table as the ultimate cheat sheet for chemistry. It tells us not just what the elements are, but also how they behave, who their friends are, and what kinds of amazing things they can do when they get together. It's like a phone book for all the atoms in existence. Every element has its own special place and its own unique story. By learning to read this table, you can start to understand the secrets of how our world works. It helps us invent new materials, create life-saving medicines, and even explore other planets. So, let's get ready to dive in and explore this incredible scientific masterpiece together. Consider the following. It's awesome. The reason the periodic table is so incredibly important is that it organizes everything so perfectly. It's not just a random list, there's a beautiful, underlying logic to its structure. This organization allows scientists, and you, to spot patterns and make predictions. You can look at an element's position on the table and know with amazing accuracy whether it's likely to be a solid, a liquid, or a gas at room temperature. You can guess if it will be shiny, if it will conduct electricity, or if it will react explosively with water. This predictive power is what makes the table an indispensable tool for chemists, physicists, biologists, and engineers. So, get excited. We are about to go on a journey through the fundamental components of everything. We'll look at the rows and columns, decode the symbols, and meet some of the most fascinating elements that play a huge role in our daily lives. Understanding the periodic table is like learning the alphabet of the cosmos. Once you know it, you can start to read the story of matter itself. And that, my friends, is what science is all about. It's about curiosity, discovery, and understanding our place in the universe. Let's go! Alright, let's break down this amazing chart. The first thing you need to know is that the elements are arranged in order of their atomic number. The atomic number is simply the number of protons in the nucleus of a single atom of that element. We start with hydrogen at number 1, then helium at number 2, lithium at number 3, and so on. As you read the table from left to right, like a book, the atomic number increases one by one. This number is the element's fundamental identity. If an atom has 6 protons, it's always carbon. If it has 8 protons, it's always oxygen. No exceptions. It's the most basic rule of the table. Now let's look at the columns. The vertical columns are called groups or families. There are 18 groups in the standard periodic table, numbered from 1 to 18. Elements in the same group are like cousins in a big family. They have similar chemical properties. This is because they have the same number of electrons in their outermost shell, which we call valence electrons. These are the electrons that get involved in chemical reactions. So everything in group 1, like lithium and sodium, tends to react in a very similar, very enthusiastic way. Everything in group 18, the noble gases, is very chill and unreactive for the same reason. It's all in the family. Next up are the horizontal rows, which are called periods. There are 7 periods on the table. As you move across a period from left to right, the elements change in a predictable way. On the far left, you have very reactive metals. As you move across, the elements become less metallic. On the far right, you find the nonmetals, and finally, those very stable noble gases we just mentioned. This gradual change in properties across a period is one of the most beautiful patterns in chemistry. Each new period represents a new energy level or shell for the electrons. It's like adding another floor to a building, giving the electrons more room to exist. So, to sum it up, the atomic number gives each element its unique spot. The groups or columns tell you about an element's chemical family and how it likes to react, and the periods or rows show you how properties change as you build up atoms with more and more electrons. This brilliant organization, first figured out by the scientist Dmitry Mendeleev, allows us to see the relationships between all the elements at a single glance. He even left gaps in his original table for elements that hadn't been discovered yet, and he correctly predicted their properties based on the patterns. How cool is that? Science rules. Every element on the periodic table gets its own special box, kind of like its personal address. Inside this box you'll find a few key pieces of information that tell you everything you need to know about that element's identity. It might look like a secret code at first, but it's actually very simple to read once you know what you're looking for. Let's take a look at a typical element box, say for carbon, the element that is the basis for all life on Earth. You'll see a big letter, a couple of numbers, and the element's full name. Each piece of this puzzle tells a part of the element's story. The most prominent thing in the box is usually the atomic symbol, which is a 1 or 2 letter abbreviation for the element's name. For carbon, the symbol is simply C. For oxygen, it's O. For helium, it's He. Notice that the first letter is always capitalized, and if there's a second letter, it's always lowercase. This is a universal system, so a chemist in Japan and a chemist in Brazil both know that Au stands for gold, from its Latin name, aurum. These symbols are the shorthand that scientists use to write chemical formulas, making it much easier than writing out the full names every time. Above the symbol, you'll almost always find the atomic number. As we learned, this is the big one. It tells you the number of protons in the atom's nucleus. For carbon, the atomic number is 6. This means every single carbon atom in the universe has exactly 6 protons. This number defines the element and determines its place on the periodic table. It's the element's unique ID number, and it's the most important piece of information for identifying it. You can always count on the atomic number to be a whole number, because you can't have half a proton. Finally, below the element's name, you'll see another number, which is the atomic mass. For carbon, this number is about 12.011. Unlike the atomic number, the atomic mass is usually not a whole number. That's because it's the average weight of an atom of that element, taking into account its different isotopes. Isotopes are versions of an element that have the same number of protons but a different number of neutrons. The atomic mass is a weighted average of all the naturally occurring isotopes of that element. It's a crucial number for doing calculations in the lab and figuring out how much of an element you need for a reaction. Now that we know how the table is organized, let's talk about how the elements themselves are sorted into different types. You can think of the periodic table as being divided into 3 main neighborhoods. The residents of each neighborhood share some common characteristics. These 3 major categories are metals, nonmetals, and metalloids. Looking at a color-coded periodic table, you can see these sections clearly. The vast majority of elements located on the left side and in the middle of the table are metals. They are the biggest group by far, and they are incredibly important to our world. Metals are probably what you think of first when you hear the word element. Think of things like iron, copper, gold, and aluminum. Metals are typically shiny, we call that luster. They are good conductors of heat and electricity, and they are usually solid at room temperature, with mercury being a famous exception. They are also malleable, which means you can hammer them into thin sheets, and ductile, which means you can draw them out into wires. These properties are why we use metals for everything from building skyscrapers and bridges to making electrical wires and jewelry. They are the strong, reliable workhorses of the elemental world. On the other side of the table, in the upper right-hand corner, you'll find the non-metals. This group includes familiar elements like oxygen, carbon, nitrogen, and sulfur. As their name suggests, their properties are pretty much the opposite of metals. They are typically not shiny, they are poor conductors of heat and electricity, and they are often gases at room temperature. The solid non-metals like sulfur are brittle, meaning they will shatter if you try to hammer them. While there are fewer non-metals than metals, they are absolutely essential for life. In fact, the elements that make up most of your body, oxygen, carbon, hydrogen, and nitrogen, are all non-metals. Between the metals and the non-metals, there's a curious group of elements that live on the border. Running like a staircase down the table, you'll find the metalloids. These elements are the fence-sitters of the periodic table. They have properties of both metals and non-metals. For example, silicon is shiny like a metal, but it is brittle like a non-metal and doesn't conduct electricity very well. Because they are semiconductors, metalloids like silicon and germanium are the heart of the electronics industry. They are the key ingredients in the computer chips that power our smartphones, laptops, and pretty much all modern technology. They are the bridge between the 2 other major groups. Let's take a closer look at the biggest family on the block, the metals. They occupy a huge portion of the periodic table for a reason. They are incredibly versatile and form the backbone of our modern civilization. When we talk about metals, we can even break them down into smaller, more specific families with even more predictable properties. For instance, the very first column, Group 1, is home to the alkali metals. This family includes elements like lithium, sodium, and potassium. These metals are incredibly soft. You can actually cut them with a knife. And they are fantastically reactive, especially with water. They have to be stored in oil to keep them from reacting with the moisture in the air. Moving over to Group 2, we find the alkaline earth metals. This family includes beryllium, magnesium, and calcium. They are still very reactive but not quite as explosive as their alkali metal neighbors. They're a bit harder and have higher melting points. Calcium is a perfect example of this group's importance. It's the element that makes our bones and teeth strong. Magnesium is a lightweight yet strong metal used in everything from airplanes to car parts to camera bodies. These metals show us that even within the larger category of metal, there are distinct personalities and uses based on their position in the table. In the center of the periodic table, spanning from Group 3 to Group 12, is a large block of elements known as the transition metals. This is where you'll find some of the most famous and useful metals we know: iron, copper, nickel, gold, silver, and platinum. These metals are generally hard, shiny, and have high melting points. They are excellent conductors of heat and electricity. Their ability to form strong alloys, mixtures of metals, and colorful compounds makes them essential for industry, construction, and art. Think of the steel, which is an iron alloy, in our buildings, the copper in our electrical wiring, and the gold and silver in our most precious jewelry. Finally, at the very bottom of the table, you'll see two separate rows that look like they've been pulled out from the main body. These are the lanthanides and actinides, often called the inner transition metals. The lanthanides are used in powerful magnets, high-performance optics, and even the screens of our televisions to produce vibrant colors. The actinides are all radioactive, and this group includes some very well-known elements like uranium and plutonium, which are famous for their use in nuclear power generation and nuclear weapons. These metals might seem obscure, but they have powerful and world-changing applications. From the softest alkali metals to the heavy radioactive actinides, the world of metals is diverse and honestly pretty amazing. While metals may be the majority, the non-metals and metalloids are just as crucial to the story of our universe and our daily lives. Let's start with the non-metals, clustered in the upper right corner of the table. This diverse group may be small, but it contains the absolute essentials for life itself. The air we breathe is almost entirely made of two non-metals: nitrogen and oxygen. Oxygen is the element that our cells use for respiration to create energy, while nitrogen is a critical component of the proteins and DNA that make us who we are. These elements are a perfect example of how non-metals are the building blocks of the living world. Another fascinating family within the non-metals is found in Group 17, the halogens. This group includes fluorine, chlorine, bromine, and iodine. The name halogen means salt former because these elements love to react with metals to form salts. For example, when the halogen chlorine reacts with the metal sodium, they form sodium chloride, common table salt. Halogens are extremely reactive and are powerful disinfectants. Chlorine is used to keep the water in swimming pools safe and clean, while iodine is used in hospitals as an antiseptic to clean wounds. They are the chemical cleaners of the periodic table. And what about that final column, Group 18? These are the noble gases: helium, neon, argon, and others. They are the complete opposite of the halogens. They are famous for being almost completely unreactive. Their outermost electron shells are full, so they have no desire to share, steal, or give away electrons. They are stable and content on their own. This property makes them very useful. Helium, being lighter than air, is used to fill balloons and blimps. Neon is the element that gives us the bright reddish-orange glow in neon signs. The noble gases show us that sometimes not reacting is just as important as reacting. Now for the in-betweeners, the metalloids. These elements, including boron, silicon, germanium, and arsenic, form a diagonal staircase separating the metals from the non-metals. Their most famous property is that they are semiconductors. They don't conduct electricity as well as a metal, but they're not insulators like a non-metal either. We can control their conductivity, turning it on and off with an electrical signal. This unique ability is the foundation of all modern electronics. The tiny silicon chip in your computer contains billions of microscopic switches made from this amazing metalloid. Without metalloids, our digital world simply wouldn't exist. Let's put some faces to the names and talk about a few of the all-star elements that you interact with every single day. First up is hydrogen, element number 1. It's the simplest, lightest, and most abundant element in the entire universe. Over 90% of all atoms in the cosmos are hydrogen atoms. Here on Earth it combines with oxygen to form the most important compound for life, water. Hydrogen is also a clean fuel source. It powers the sun through nuclear fusion, and is used as a rocket fuel by NASA. It may be first on the table, but its importance is second to none. It's the true number one. Next, let's talk about carbon, element number 6. If hydrogen is the king of the universe, carbon is the king of life. It has an incredible ability to form strong bonds with itself and many other elements, creating long, complex chains and rings. This versatility allows it to form the backbone of all the organic molecules that make up living things: DNA, proteins, fats, and carbohydrates. From the graphite in your pencil to the diamonds in a ring, carbon shows up in many forms. It's the ultimate building block, proving that from one simple element, endless complexity can arise. Let's float on over to helium, element number 2. Helium is the second most abundant element in the universe, forged in the heart of stars like our sun. It's a noble gas, which means it's very light and doesn't react with other elements. We know it best for its use in party balloons and blimps, but it has some seriously cool scientific uses too. Liquid helium is one of the coldest substances known, and it's used to cool the powerful superconducting magnets in MRI machines at hospitals, which allow doctors to see inside the human body without surgery. Helium is more than just a party trick, it's a high-tech wonder. Finally, let's consider a truly essential metal iron, element number 26. Iron is the workhorse of human history. The discovery of how to extract and use iron ushered in the Iron Age and changed civilization forever. When mixed with carbon, it creates steel, the strong and affordable alloy we use to construct everything from cars and ships to skyscrapers and bridges. But iron is also essential for life. It's the central atom in the hemoglobin molecule in your red blood cells. Its job is to grab onto oxygen in your lungs and carry it to every cell in your body. Without iron, we literally couldn't breathe. One of the most powerful things about the periodic table is its ability to help us predict how elements will behave and react with one another. Chemistry is all about how atoms connect to form new substances, and this process is driven by electrons, specifically the electrons in the outermost shell, the valence electrons. The periodic table's structure gives us major clues about these electrons. As we discussed, elements in the same group or column have the same number of valence electrons. This is why they act like a family and have similar chemical properties. They all want to achieve a state of stability, like their cool cousins, the noble gases. Think of it like this. The noble gases in group 18 have a full outer shell of electrons, which is a very stable and low-energy state. They're happy as they are. All the other elements are striving to get that same stable electron arrangement. The alkali metals in group 1 have just one lonely electron in their outer shell. The easiest way for them to become stable is to give that one electron away. This makes them very generous and highly reactive. On the other hand, the halogens in group 17 are just one electron short of a full shell. They are electron thieves and will aggressively try to grab an electron from another atom to complete their set. This is where the magic happens. When an element that wants to give away an electron, like sodium from group 1, meets an element that wants to take an electron, like chlorine from group 17, it's a perfect match. Sodium happily gives its single valence electron to chlorine. Now, both atoms have achieved a stable, noble, gas-like electron configuration. In the process, they become charged ions and stick together through an electrical attraction, forming the compound sodium chloride, or table salt. By simply looking at their positions on the table, we could have predicted that this reaction would happen. It's chemistry matchmaking. This predictive power extends across the entire table. We can predict that elements on the far left, the metals, will tend to react with elements on the far right, the nonmetals. We can predict that elements in the middle might share electrons instead of giving them away. This understanding of patterns allows chemists to design new molecules and materials. They can intelligently mix elements, knowing how they are likely to interact, to create everything from stronger plastics to more effective medicines. The periodic table isn't just a list, it's a dynamic map that guides us through the dance of chemical reactions. It lets us see the future, chemically speaking. So, why should you spend time learning about the periodic table? Because it's more than just a chart in a science book. It is a story. The story of our universe and everything in it, including you. Every element on that table, from the hydrogen in the water you drink to the calcium in your bones and the iron in your blood, was forged in the heart of a star, or in the explosive death of one. When you study the periodic table, you are learning about your own cosmic origins. You are, quite literally, made of stardust, and the periodic table is the cast of characters that make up your existence. Understanding the periodic table empowers you to be a more informed citizen of the world. It helps you understand headlines about nuclear energy, uranium, plutonium, climate change, which is all about carbon, and new technologies like silicon and lithium. It helps you read the ingredients on your food label and understand the difference between sodium and sodium chloride. It demystifies the world around you, replacing confusion with curiosity and understanding. When you know the basics of the elements, you can ask better questions and make more informed decisions about your health, your environment, and the technology you use every day. It's a fundamental piece of scientific literacy. For students, the periodic table is the gateway to all the sciences. You cannot truly understand biology without knowing about carbon, oxygen, and nitrogen. You can't understand earth science without knowing about silicon, oxygen, and iron. You can't understand physics without knowing about radioactive elements and the structure of the atom. The periodic table is the common language that connects all these different fields of study. Mastering it is like getting a key that unlocks countless doors to deeper scientific knowledge. It builds a foundation of critical thinking and pattern recognition that will serve you well, no matter what you choose to study. Ultimately, learning about the periodic table is an act of wonder. It's a chance to appreciate the incredible order and elegance of the natural world. It shows us that from less than 120 basic ingredients, an infinite variety of substances can be built, from a simple grain of sand to the complex machinery of the human brain. The universe is an amazingly intricate and beautiful place, and the periodic table is our human-made key to understanding its fundamental logic. So, be curious, keep asking questions, and explore the elements. Because science, my friends, really does rule,